Hello everyone, welcome to our lecture series of Structure 2. So as discussed in our previous video, we were solving this example of the beam where we had in our first video we had taken the reaction at roller A as redundant. So in this case scenario, we will be taking the moment. We will take the moment at fixed A as redundant. So if you have not seen my previous video, my video one is related as introduction to method of constant deformation. So do check out that video. You can check out my video 2 as well, which you can find in the description below. And for more detailed course on structural analysis, you can check my Udemy courses. So let's move on to our case. So I've already discussed all about this in my video, in my first video. So in the case scenario 2, what we're going to do is we're going to take a moment at A as redundant. So let me draw my original beam. Here is A, here is B. So we have a moment acting over here. We have 1 2 3 reaction here and 1 4. So in previous case scenario we took a reaction at B as redundant. In this case scenario we're going to take a moment. We're going to take moment at A as redundant. So if we remove this rotation or the moment at end A, our beam, so how we can draw our beam in this manner. There is certain load acting over here. As well as support B. This is A. The our fixed beam will our fixed support will our fixed so our fixed support. If we remove the moment, if we take moment as redundant, we will have a hinge support at A, hinge support at A, and we will have a deflection in such manner, and we're going to take this slope at point A, which is going to take on as theta A. So we have written theta A naught over here. As you can see, we have written theta A naught over here. Now we have second. So this is our primary beam subject to external load. So external load is 24 kN per meter. This will be our case scenario when our primary beam is subject to external load. So as you can see, we can also calculate the support reactions AY naught and BY naught, which should be equal to 120 kN, because we have a total span of 10 meter. We have our total span of 10 meters. So there are only two forces acting upward. So the force will be divided equally. So we can write reaction at A, RAY plus RBY equals to 24 into 10. Since there are just we also have another relation, which is forces acting upward or downward. We can take any relation, which is RAY plus RBY equals to 240 into 10. RAY plus RBY equals to 240. So in this case scenario, we can directly write we can write RAY equals to RB equals to minus RBY, because there are just only two forces acting in this case scenario. So it's just a simple trick. So we have our value of RAY as 120 kilonewton. So in our case scenario, so in our okay, so let me write over here 120 kilonewton. So in our case scenario where only two forces are equal, they will be equal and opposite in direction. Sorry, they are acting in same direction in this case scenario. B naught y also equal to, because summation of these two forces needs to be equal to 240 kilonewton. So now next we have our primary beam subject to unit redundant. So now previous case scenario where we took support at B, where we took support reaction at B as a redundant. In that case scenario we applied our unit load at B. So in this case scenario where we have taken moment at A, we have taken moment at A as moment at A as redundant. So what we will be doing is we will take unit moment. We will take unit moment at point A. So as shown in this so as shown over here. So what we will be simply doing is we will take a moment. Unit moment at point A, which has value of 1 kilonewton meter. So 1 kilonewton meter. In that case scenario, we will have our deflection in this way. In this way, we can write the value of AYA as 1 by 10 and BYA equals to 1 by 10. So if I draw my beam in this way, we have 1 kilonewton meter acting over here. So there is hinge support. Since I remove the fixed remove the moment reaction, we will have hinge support over here. So what we can do is my point A, we can take point B. We have A Y, we have B Y. So what we can do is I can take clockwise moment about A equals to 0, and if I take this way, upward force as positive By, we can take any sign, we get Ay equals to minus by, Ay plus By equals to 0. So if I take moment at A equals to 0, since we are acting in anti-clockwise, so we can assume in any direction. We normally assume in anti-clockwise direction, so we get minus 1. AY will not produce any sort of movement at A, because the distance of a reaction, the direction of the reaction force AY from point A is 0. So what we can do is, this is trying to turn the beam in this direction, which is anti-clockwise direction. So again, I need to uh, write this as negative minus by into 10 equals to 0. So I get this value as by equals to minus 1 by 10 kilonewton, and I get from here ay plus by equals 0. So ay is 1 by 10 newton. So I get this direction. So we initially assume the direction of by to be upward. So the actual direction of actual direction of by is downward. So as you can see, by is 1 by 10 and aya. So aya means A is the reaction at reaction at a support reaction at support A when unit moment is applied at A. So similar BY also means reaction force at B when unit moment is applied at A. So now we'll apply this relation, this compatibility equation, which is theta a naught is this value plus f a a is the slope over here due to unit moment ma equals to 0. So initially we applied this relation del b naught plus fbb dot by equals to 0. So in this case scenario, when we are taking moment as written, we won't take deflection, but we will take slope. So what we're going to do is we're going to take theta a naught plus f a dot ma equals to 0. So now we have so this is from our virtual work method. So we have these formulas from virtual work method, as I explained in my previous videos. This we have theta a naught. That's the person. We have theta a naught equals to m naught ma divided by ei dx, whereas faa equals to ma square divided by ei dx. So I've already explained what is m naught ma, what is ma. M naught is the bending moment at any section due to external load, bending moment at any section due to external load, whereas ma is bending moment at any section due to unit load. So firstly, let's find out our values. So we need to find out our values for m naught and ma. So firstly, what we're going to do is we're going to take a segment ab. So let me so we have this figure. We can put both of these side by side, so it will be easier for us to read over here. So firstly, what we are going to do is we are going to look at segment AB. So this is our segment AB. Segment A segment AB. We can take origin at either A, or we can take origin at either A or either at B. So currently we are taking origin at A. You can take origin at B. In our previous example, we had taken origin at B. So our limit is our limit of x values, which varies from 0 to 10, which varies from 0 to 10. So firstly we have m naught. We're going to take m naught is bending moment at any section due to external load. So we need to look at our this first figure, bending moment at any section due to external load. So we are going to take a section x, which is at from point a. So we have our value of ay naught as 120. I will explain how we obtained these two values. So if you look at point x, it is going to produce upward moment. So what we're going to do is we're going to take clockwise moment as positive. So this is going to produce clockwise moment at that point. So we're going to get a value positive. So 120 is into x. Whereas 24, this UDL is acting downwards, which is going to produce anti-clockwise moment with reference to this section, with reference to this section at point x. So it's going to be minus 24 into, it is acting over a span of x, and UDL will always act at a distance of half of the span, at a distance of x by 2 equals to on distance not equals to 0. So we get 120 x minus 12 x squared. So for this you have understood how I have calculated this. Simply I'm going to take a bending moment with reference to this any point, difference to this point. So m naught basically is bending moment at any section due to external load. So we have our value of 120 into x minus 24. Another is UDL. UDL is acting in this way. If I convert UDL, this is my UDL. If I convert UDL, let me write this as x, and it is acting at distance y. If I convert my UDL into point load, it will be the value of the point load will be x into y. Whereas y is the span, it will act at the half the span of y by in this manner. So I have done this as over here. 24 into span x into, it will act at a distance from half the span, which is x by 2, and it's going to produce anti-clockwise moment. So 120x minus 12 x square. So we have completed our calculation for m naught. Now next we'll be finding out our calculation for ma, which is bending moment, which is the bending moment at any section due to point load, or in our case due to unit rotation. So we're going to look at this figure. So again we're going to take a section x over here. So if we look at the bending moment, so in this section what we're going to do is this is going to produce upward moment 1 by 10 into x. So we have firstly 1 by 10 into x, 1 by 10 index. So this is producing right now clockwise moment. So clockwise moment are taken as positive while moving from left to right. So I already explained in my previous video, while moving from left to right portion of a beam, clockwise moment are taken as positive, while moving from right to left, clockwise moment are taken as negative, whereas vice versa, whereas anti-clockwise moment are taken as negative, whereas vice versa. For this, clockwise movement are taken as negative, anti-clockwise movement are taken as positive. So you need to remember this one. Moving from left to right, clockwise positive, anti-clockwise negative, vice versa for right to left. So right now we are moving from left to right. So 1 by 10 into x, clockwise movement positive, while previously we took the value of 1 kilonewton meter in anti-clockwise direction, which is going to be negative. So 1 by 10 into x minus 1, 1 by 10 into x minus 1, which is x by 10 minus 1, is going to be our value for ma. So we have the value of m naught, we have our value of ma. So we have our formula of theta a naught. So theta a naught will be equal to m naught ma divided by ei dx. Our limit is 0 to L. So our limit is 0 to 10. We have our value of m naught, which is 120x minus 12 x square, when our ma is x by 10 minus 1 divided by ei dx. On solving this, we're going to get the value of minus 1000 divided by ei. So this is a really simple to solve. So hopefully we can solve this by 0 to 10. We have 120 x minus 12 x square. This is x minus 10 divided by 10 ei. So you need to multiply this, and this is a simple mathematics. So hopefully we can do this. If you have any queries regarding how we got the value of minus, this is just simple and derivative. Hopefully we can do it. So next we have FAA, which is the formula for FAA is limit 0 to 10 MA, which is x by 10 minus 1 whole square divided by dx divided by ei. So this is 0 to 10, x minus 10 divided 10 square is 100 comes outside, x by 10 whole square divided by, so this is a minus b whole square, which is x square minus 20x plus 10. So again you can solve this comes as x cubed by 3 minus 20x square by 2 plus 20x limit of 0 to 10. So apply this simple algebra, apply this simple and derivatives, and you're going to get the value as 3.3 divided by ei. So after solving all this, what we're going to do is we're going to get into our main agenda of our formula, which is theta a naught plus f a dot ma moment about a equals to 0. So ma is equivalent to the reaction moment reaction which we had at the support a ma. So we have our value of 10, we have our value of fa. Simply we put and we get our value of fa ma as 300 kilonewton per meter. So in order to remove in order to convert this in order to remove that redundant moment, we have to apply a moment of 300 kilonewton meter, which is equivalent to that. So after knowing this, what we're going to do is we're going to simply put that value. So this becomes our equation now. 24 kilonewton meter is 24 kilonewton per meter. UDL is acting over here. A B. So I need to find the value of AY and BY. We have found the value of MA to be equivalent to 300. I think 300, yes, 300 kilonewton meter. So let me write it over here, 300 kilonewton meter. But what we can do is we can take moment about A, or we can take moment about B equals 0. So in this case scenario, they have taken moment about b equals to 0. So this is acting in anti-clockwise direction. Its value will be negative minus 3000 plus ay. This is acting in clockwise direction, so positive ay into 10. By will not produce any moment at a b since the distance is 0. uh, 24 is acting downward, so it is going to produce minus 24 into span is 10. It will act at a distance of 10 by 2 as I explained before. And on solving this, we are going to get value of ay as 150 kilonewton. Similarly, we will get we can use the formula ay plus by equals to 24, equating all the forces in y direction into 10. So I get my value of by as 90 kilonewton. So I have written here my value of ay 150 and by 90. So after having all these values, so we had obtained the same value of ay and by by taking support at reaction b as redundant. So next what we need to do is we need to draw the shear force diagram and bending moment diagram. So this is my actual beam. Just it over here. So this is my actual beam. So what we're going to do right now is we're going to draw the shear force diagram. So we have value of ay as 150 kilonewton. So in order to draw the shear force diagram, so right now we have the value of ay as 150 kilonewton. So this will go upward. Ay equals to, we have 150 kilonewton. Since this is acting upward, it will push it upward in this way. So it's not a straight line. Ay is 150 kilonewton, and since the UDL is acting downward, it will decrease the force value, and it will get ultimately pumped up over it, and it will get increase back to 0 at here B. And this value will be equivalent to 90 kilonewton, which is my by because there will be a minus 90 over here, plus 90 will push it upward and make it 0 at b. So next we need to find this point where shear force where this value will be 0. So we can take this as x from point A, and this will be 10 minus x. So we can use the equation of similar triangle. X by 150 equals to 10 minus x divided by 90. On solving this, we get the value of x as 6.25 meters. So this will be at 6.25 meter from point A. The shear force will be 0. Next, we need to draw our bending moment diagram as well. This is now for our bending moment diagram. We have our value of moment at A. The value of moment at A was, we calculated it to be 300 kilonewton meters. So it is acting downward. Sorry, it is acting in anti-clockwise direction. So we have a certain sign convention for bending moment diagram as well. So in our shear force diagram, above this line it was taken as positive, while below was taken as negative. Whereas same for bending moment diagram, below the line we are going to take negative. So we have this value as 300 kilonewton meter, since it is acting in anti-clockwise. So the moments acting in anti-clockwise direction are taken as negative. So we will put minus over here, minus over here, and wherever the shear force is uh, 0. Okay, so what we're going to do is we're going to since there is UDL is acting over here, so we need to know the simple logic for bending moment diagram for UDL is we will have this type of diagram whenever UDL is acting. Uh, so what you can do is it will go on increasing in certain way, and it will make a certain slope in this way. So this will be at wherever the shear force is 0, the bending moment will be maximum. So this will be at point of x equals to 6.25 meter, the bending moment will be maximum. So we can find find the value of bending moment at 6.25 meter, which will be negative positive. So what we can know is the simple logic for our bending moment diagram whenever a tutorial is acting in this way. So this value will be, I think, w square by 8, w square by 8, which is w is 24 into l is 10 square divided by 8, 8 3 is 24, which is 300 kilonewton meter. But due to the influence of 300 kilonewton meter, but due to influence of ay, this will get decreased to some extent. So in order to find the value at over here, what we can do is since at a distance of 6.25, so this will be equal to 150. We have a force acting over here as 150 ay, 150 into, so this is acting upwards, so to produce clockwise moment. 150 into 6.25 minus w is 24. 24 into distance is 6.25 whole square by 2. This is w into l into again l by 2, so it's just simply w square by 2. So if we multiply this, we're going to get the value as 168.75 kilonewton meter. So we can check this. So hopefully you have understood how to draw the shear force and bending moment diagram as well. So you need to understand basics of how the bending moment diagram will be when different kinds of loads are acting, so it will be easier for you to draw this diagram. So hopefully you have understood our first basic example on how to solve any beam, any indeterminate beam by using method of constant deformation. So if the video was helpful, do like the video, do follow our playlist for more videos, and do subscribe to our channel. Thank you.